In today's lesson, we're going to begin looking at chemical bonding, or what happens when elements form compounds. Chemical bonding, what exactly is a chemical bond? The short answer to that question is that a chemical bond is a force of attraction between atoms. It is not a physical structure, it's actually a force of attraction. That force is due to an attraction between oppositely charged objects. So we have the nucleus of an individual atom attracting the electrons of a second atom. So when we bring two atoms together, each atom's nucleus attracts the electrons of the other atom, resulting in them being held together. So why do atoms do this? Why don't atoms just stay pure? There are very few elements that exist pure in nature. The big reason is that atoms don't tend to be energetically stable. They have a tendency to lower their potential energy when they bond with other atoms. So bonding has the effect of lowering energy and results in greater stability between the atoms that are involved. Stability is the key, and the key to stability is lowering your overall potential energy. So what is formed when atoms bond? There are two different levels of answers to that question. One is that we would form a compound, which we classified matter before, so we know that a compound is a pure substance made of at least two elements. We could also say, however, that a molecule is formed. That's one possibility. A molecule is a group of at least two atoms, and they may even be of the same element, such as oxygen forming O2 or hydrogen forming H2. So when atoms bond, we can classify the types of bonds that form. There are three types of bonds that include ionic, covalent, and metallic. We'll have a section in upcoming videos on both ionic and covalent bonds with some discussion of metallic, but very little. So how do we classify ionic versus covalent versus metallic bonds? We classify them according to how their electrons are arranged whenever the atoms come together. So in general, how do we decide the bond type? And what do we look at in terms of electron arrangement? Well, one thing is that we would look for location on the periodic table. Location on the periodic table, if we have a wide separation between them, such as a group 1 and a group 17 atom, such as sodium and chlorine. In a situation like that, there should be a large difference in attraction for electrons. That attraction can be measured in multiple ways, but there is a large difference nevertheless. Elements that are close together on the periodic table tend to have similar properties, more similar properties than those that are widely separated, and therefore they have similar attraction for their electrons. Whenever we're looking at a wide separation, generally speaking, this large difference in attraction leads to electrons being transferred. Electrons being transferred result in ionic bonds. We end up with positive and negative ions forming. Elements that are close together on the table tend to have similar attractions for electrons, and that means that electrons, instead of being transferred, are going to be shared. And at least one way of our typical way of sharing is what we would call the covalent bond. But we also have another way of sharing when they're close together on the table, and that could also be metallic. Because the electrons are shared in something known as an electron sea, SEA, which we'll talk more about later. So let's suppose we have metals and nonmetals. So we can think about this in terms of location on the periodic table, but first metals and nonmetals. Metal and nonmetal compounds have wide separation, two different sides of the periodic table. Therefore, the electrons are transferred, and we have ionic bonds, as we set up here. If we have two nonmetals, those compounds are going to contain two nonmetals, therefore they're close together on the periodic table. The electrons are shared, and we end up with covalent bonds. If, on the other hand, we have two metals in combination, they're also close together on the periodic table, and we would call that metallic bonding. The sharing is still there, but it's in a different way. It is not what we would typically think of as being a covalent bond. So what specifically decides bond type? First answer to that is the difference in electronegativity. There's more to it than that, but electronegativity is probably the easiest one to look at. We know that electronegativity is a measure of the strength of attraction of an atom for a bonded pair of electrons, or the attraction of electrons in a chemical bond. So if the difference in their electronegativity is less than or equal to 1.7, we classify that as covalent. If, on the other hand, the difference is greater than 1.7, we classify as ionic. And what we find is that we get a scale of difference in electronegativity that goes from 0 to 4. Okay. And we have somewhere in here a difference of 1.7. So if we're in this zone on the periodic table, we're covalent. But if we're in this zone, we are ionic. It is possible to have a difference of 0. For instance, if we have two atoms of the same element, hydrogen bound to hydrogen, the difference in electronegativity between these two would be 0, so that would be what we would consider 100% covalent. Okay. A difference of 4 is not possible because to have a difference of 4, we would have to have an atom that has a 4, which is the maximum. That would be fluorine. And we would have to have an atom that has 0, which would be nothing, because no atom has an electronegativity of 0. So 4 is not possible, even though it's on the scale. This would be 0% covalent. We could also call this 100% covalent. We could also call this, or 100% covalent, 0% ionic. And this one would be 100% ionic. This 1.7 represents a 50-50. This is 50% covalent, 50% ionic in nature. So when we classify, we basically take their electronegativities, subtract the two numbers that are involved, and if the number is greater than 1.7, we call it ionic. If it's less than 1.7, we call it covalent. So let's look at covalent bonding. What exactly is a molecule? Molecule is a group of covalently bonded atoms. But what actually happens energetically when a chemical bond forms? Well, what happens energetically is that we have a lowering of energy. That doesn't matter if it's ionic or covalent, but covalent does result in a lowering of energy and an increase in stability. So whenever we have a covalent bond, how many electrons are there per bond? The answer to that is 2 electrons. Every covalent bond is going to have 2 electrons. Then we also have the ability, different atoms have different electronegativities, so we don't necessarily have to share them equally. And so what we would look at here, if we have something like two hydrogens, hydrogen and hydrogen, if we were to look at their electron clouds, or the electron cloud that exists in the space in between, we may have something that looks sort of like this, sort of football shaped. It's densest right through here. It's the fat area of the bond, and then it sort of drops off into a tapered area out here. The thicker the area, the more likely of finding the electron in that location. So where we would expect to find the electrons here is somewhere in between. They're most likely to be found in this zone in between. This is equal sharing. And if we had something like hydrogen bound to chlorine, we would find that because chlorine has much higher electronegativity, this would be low electronegativity. Relatively speaking, hydrogen isn't necessarily low, it's just lower than chlorine. The electrons are shifted toward the more electronegative atom. This makes this end of the bond more negative and this end more positive. So in a situation like this, we have a positive pole and a negative pole. And we say that our bond is a polar covalent bond. In this case, we have no positive and negative poles, so we call this a nonpolar covalent bond. Then we have to question, how do we decide if we have polar versus nonpolar? Well, we have our electronegativity difference of 0 to 4. And we recognize that 1.7 is halfway in between, so we have ionic here, covalent here. If we subtract the electronegativities and find that the difference is 0.3 or less, this zone from 0 to 0.3 is nonpolar covalent. This zone from greater than 0.3 up to and including 1.7, this is polar covalent. This classification of bonds has a big effect on how molecules actually behave when they're in groups. So we'll need to continue to look at this. But again, if you subtract electronegativities and it's less than or equal to 1.7, covalent. Greater than 1.7, ionic. If you're on the covalent side, if the difference is less than or equal to 0.3, it's nonpolar covalent. If it's between 0.3 and up to and including 1.7, we would call it polar covalent. Polar covalent has unequal sharing, whereas equal sharing is going to be our nonpolar covalent bond. All right, so how do we represent molecules? We represent them with chemical formulas and structural formulas. First with chemical formulas. So we represent molecules with chemical formulas and structural formulas. Here's the difference between the two. First with a chemical formula. Chemical formula would be something like H2O. What this formula shows you is it shows you the kind of atom and how many. So we have 2 hydrogens and 1 oxygen. Okay. We also have structural formulas. Structural formula for water would look like this. So the structural formula shows type of atom, number of atoms. So we can see that we still have 2 hydrogens and 1 oxygen. It also shows you the physical connections. Shows you which atoms are bonded to which. Okay, let's talk about naming compounds. So in order to be able to do much with chemical compounds, we need to discuss how we name them. And if we have a name, how do we write the chemical formula? Okay, to do this, we're going to go through something known as the chemical nomenclature system. Chemical nomenclature is just naming chemical formulas and writing chemical compounds. We start out, there are multiple types of compounds. Since I'm starting with covalent compounds, we're actually beginning with something that would be known as a type 4 compound. These are binary molecular compounds. Binary means 2, molecular means covalent. So we have 2 elements with covalent bonds. How do you recognize this? Well, we know that if we have 2 nonmetals with a difference in electronegativity less than or equal to 1.7, then we have covalent bonds. We name these using Greek prefixes to indicate the number of atoms or number of moles of atoms present in the compound. So to name these, we write the name of the positive element preceded by a Greek prefix indicating the number of atoms. We add the name of this element with the negative oxidation state and with the Greek prefix and IDE as a suffix. Now this positive versus negative. Whenever we're looking at the positive, this would be lower electronegativity, and the one that's negative would be higher electronegativity. The prefix that we use for 1, which is mono, we do not use that with the first element. So mono is only used with the second element, which would be the one with the higher electronegativity. Okay, our Greek prefixes, mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, undec, and dodec are the only ones that we'll ever need. Make sure you know your Greek prefixes. So let's look at naming type 4 compounds. And we have a chemical formula given to us and we have to write the name. First, we recognize that we've got carbon and oxygen. The first element in the formula equals lower electronegativity. So lower electronegativity or negative electronegativity, or higher electronegativity, not more negative, but just more electronegative. And so we would have name this one. We have carbon. We've got oxygen present, so we're going to say di-ox, and then we're going to modify the ending to IDE. The negative form of oxygen, which is O with a -2 oxidation state, is what this is called. is going to be called oxide. And we have two of those, so dioxide. P2O5, we have two phosphorus, so we would call this diphosphorus. 5 is pent or penta oxide. And in most cases you will see the A left off of penta before the O on oxygen. SF6, we have one sulfur, so no mono, we just write sulfur. 6 fluorine. Fluorine is a -1 oxidation state, which is the negative form of fluorine. It's called fluoride. So this would be sulfur. Prefix is hexa for 6. Hexafluoride. And then we have this one, which to begin with looks like dihydrogen monoxide. But we do not call it that. Whenever you see H2O, it is water. And we also have this one, looks like nitrogen trihydride. Which actually the better name for this would be trihydrogen nitride. It's an unusual compound. It does not go by this name. It goes by the name ammonia. These two we use as a precedent. The historical name takes precedent over any systematic chemical name. So water and ammonia. Both of these are very common compounds in chemistry, and you would need to recognize both of them. All right, writing chemical formulas for type 4 compounds. The prefixes tell you the subscript in the formula, so these are very easy. You don't have to look up these things called oxidation numbers, which you don't even know what they are yet. So, and we'll be getting to that as we move forward. Examples include dinitrogen pentoxide. Our prefixes are di and pent. So dinitrogen, N2, pentoxide, O5. Sulfur dioxide. No prefix on sulfur, so we just write S. That's one of those. And dioxide, O2. Iodine heptachloride. No prefix on iodine, so if there's just one iodine. Heptachloride, hepta is 7, Cl7. Another common type of compound that is covalent would be the acids. Okay, acids are compounds containing hydrogen. These ionize in water to make H+ ions. This is known as the aqueous definition of an acid, also called the Arrhenius, depending on your pronunciation, definition of the acid. So again, an acid is a covalent compound, always, which when dissolved in water produces hydrogen ions. So we know hydrogen has to be present. A binary acid, binary again means 2, is going to be an acid that contains hydrogen and a nonmetal covalently bonded together. To name these, the naming rule is that we always begin with the prefix hydro, we're going to have the suffix "ic," acid. The blank between the prefix and the suffix is called the stem of the nonmetal other than hydrogen. So we'll see how that's used in just a moment. How do you recognize these? Two nonmetals, one is hydrogen. There's some examples. HCl. Okay, we have two nonmetals, hydrogen and chlorine, and that makes it an acid. Since it has only two elements present, it's this type of acid, a binary acid. So we will name this hydro something ic, and then the word acid. What goes in here is chlor. So this would be hydrochloric acid, chlor named after Cl. Next we have H2SE. So our hydroic acid, selen is the root of selenium, so this would be hydroselenic acid. H3P, hydroic acid. And this would be hydrophosphoric acid. And HI, hydroiodic acid. Hydroiodic acid. So writing formulas going in the opposite direction. How do you determine which elements are present? Okay. First of all, hydrogen is always going to be present. So we know hydrogen is going to be present in a positive 1 state. Always. The other element is going to be a nonmetal. And that other nonmetal will be a non-hydrogen. It's a negative oxidation state. So let's spend a few moments discussing these things called oxidation states. Okay? So oxidation states, sometimes called oxidation numbers, and I'm just as likely to call it an oxidation number as I am state, is a number that describes the arrangement of atoms in a chemical bond. Now that seems a little bit abstract, but it's really not that difficult. We've actually already done this when we looked at ionization energies and likely charges that would be formed. The oxidation state could be considered a charge. In fact, the oxidation state and the charge of an ion are the same. In covalent bonds, we assign the more electronegative atom the negative oxidation state. So it's important to recognize your trend in electronegativities, because we have more electropositive and more electronegative atoms combined together. The atom that's more electropositive is given the positive oxidation state. And all that means is that in the electronegative, the electrons shift toward the more electronegative atom and away from the more electropositive atom. So this ends up being more than likely, when we have a scenario like that, we could have a polar covalent bond, for instance. The oxidation states that we will use are listed on your periodic table, but we'll also go through an exercise to show how to determine those oxidation states a little bit later. They are related to how many electrons must be lost, gained, or shared when forming a bond. So when we're looking at something like oxygen, and we say that oxygen has an electron configuration of, so that would be helium 2s2 2p4. That would give us an electron dot diagram of s2 p1 2 3 4. In order to, if we're going to be gaining electrons or sharing electrons somehow for this oxygen atom, the intent is to gain, lose, or share until you get an octet. That octet can be acquired by acquiring or sharing 2 electrons. When that's done, since there are 2 extra electrons in this shared arrangement, we would say that that has a -2 charge. Now, where do those 2 electrons come from? Well, if we have something like hydrogen, which has 1 electron, and an oxygen, which has 6 electrons, then we have a shared pair here, and we can add another hydrogen here to give a shared pair. And this would represent 1 covalent bond, 2 covalent bonds, but the electrons are going to shift because of the more electronegative atom, meaning oxygen. This is the more electronegative atom, so this means that we have these 2 extra electrons from hydrogen shifting toward the oxygen. That gives it a -2 charge. Each hydrogen has 1 electron shifting away from it toward the oxygen, giving it a +1 charge. But you'll notice that we have 2 positives and 2 negatives. So an important feature of oxidation states in compounds is that the sum of oxidation states equals 0 in a compound. So let's go back to this slide. Hydrogen in acids is always going to be the positive oxidation state, specifically hydrogen with a +1 charge. The other nonmetal is going to be the negative oxidation state. When we say we combine using oxidation numbers, that means we combine to produce a neutral molecule. So as an example, if we have hydroarsenic acid, okay, we know with this we're going to have hydrogen. Hydrogen has a +1 oxidation state. We're also going to have arsenic. Arsenic is going to have a -3 oxidation state. So when we're looking at this, we're going to counteract this -3 to combine with 0. We're going to have 3 of these +1s. So we would have to have hydrogen, hydrogen, and hydrogen. We would have to have 1, 2, 3 hydrogens to give 1, 2, 3 positives to counter the 1 -3. So this would give the chemical formula H3AS. Another way to look at that is that if we look at arsenic and you do its dot diagram, it would look like this. So when we look at hydrogen, we bring in a hydrogen, 1 electron, 1 electron, 1 electron from each of the hydrogens, and you'll notice that that gives this compound something known as an octet. So arsenic now has 8 valence electrons, and each hydrogen has 2 valence electrons. In either case, this is going to be a satisfied set of atoms because arsenic prefers to get 8, like a typical noble gas. Hydrogen gets only 2 because it's small, so it develops the noble gas electron configuration that resembles helium. Okay, so if we look this up, and we find that hydrogen is a positive 1 and arsenic is a negative 3, an easy way to handle this in formula writing is to take your 1, the charge of hydrogen, or the oxidation state of hydrogen, and bring it down here as a subscript for arsenic, and then take the 3 without the negative, just the 3, and bring it over to the hydrogen as the subscript, and then rewrite, when you rewrite it, H3AS, the 1 is understood, that's the proper formula for this acid. Okay, hydrobromic acid. We know we have hydrogen and we have bromine. Hydrogen is a positive 1, bromine is a negative 1. So we're going to have H1Br1. Positive 1 and negative 1 cancel. Then we have hydrotelluric acid. Bring this over here. This is going to have hydrogen, positive 1, and tellurium with a negative 2. So if this is positive 1, we bring our 1 over to tellurium. We bring our 2 over here. This is given as a common multiple. And this is going to be 2 there, 1 here. And we rewrite as H2TE would be hydrotelluric acid. Okay. We also have ternary acids. Ternary acids are called oxoacids, sometimes called oxyacids. And these are going to be acids that contain hydrogen covalently bound to an oxygen that contains a polyatomic ion. A polyatomic ion is a group of atoms with charge. Examples would include things like SO4, which is called sulfate, has a negative 2 charge. PO4, which is phosphate, it has a negative 3 charge. SiF6, a negative 2 charge, that's hexafluorosilicate. CO3, negative 2 charge, that's carbonate. So we have lots of polyatomic ions, and you will be receiving a list of polyatomic ions in your paperwork in class. To name oxoacids, the name is based on the polyatomic ion, so it's important to know or have your list of polyatomic ions. If the polyatomic ion ends in ATE, such as carbonate or phosphate or sulfate, you write the name of the polyatomic ion. In general, drop ATE and add IC, then add the word acid. If the polyatomic ion ends in ite, ITE, we write the name of the polyatomic ion, we drop the ITE and add OUS. Okay? So let's look at, and then add the word acid. Hydro is not used with these acids. If hydro is used, it's a binary acid. So examples. Have HClO3. Everything but the hydrogen is the polyatomic ion. So we have ClO3, which has a negative 1 charge. This is called chlorate. Chlorate ends in ATE. So to name this acid, we know it's an acid because it has hydrogen with this negatively charged group of atoms. So we would call this chlor, drop ATE, add IC, chloric acid. HClO4. ClO4 is perchlorate. So this becomes perchloric, drop 8, add ic, and then add the word acid. H3PO4. The PO4, the -3 charge, is phosphate. It ends in ATE, so we're going to drop 8 and add IC, but there's a little more to this one. This is the reason that it's here as an example. Still an ic acid, phosphoric acid. And we have H2SO4, another one that's a little bit different. SO4 is sulfate. Because it ends in ATE, we know we're going to have an IC ending on the acid, but rather than sulfic, this is sulfuric acid. And let's do one more. Let's do HNO2. NO2 with a -1 charge is nitrite. It ends in ITE. ITE converts to OUS, so this is going to be nitrusite to us acid. Then we have formula writing. There's nothing new here, still combining using oxidation numbers. Some examples. We have arsenic acid, so we've got the name. Since there's no hydro, we know that this is a ternary acid or an oxyacid. This is going to be hydrogen. That comes from the word acid. We know hydrogen is going to be there with a +1 charge. Arsenic has to have come from arsenate. So we're reversing. We're taking ic and we're going to ate. Arsenate is AsO4. So we look this up and we're going to find that this has a -3 charge. So this is going to be, we have a +1 and a -3. So this is going to be, bring the 3 to hydrogen, H3, bring the 1 to arsenate. But it is important to note that in the arsenate, we're saying that we have 1 of everything there. So I've got parentheses there. These parentheses are not needed in this specific case, but we're saying we have 1 of everything here. So the final formula is actually H3AsO4. Nitric acid. Okay, we know that we have hydrogen. Nitric came from nitrate. Nitrate, we look up and we find that we have NO3, the -1 charge. So we've got +1, -1. That's a 1-to-1 ratio to give neutrality, HNO3. Nitrous acid we just did. That's going to be hydrogen. And we have nitrous. Us came from ite, so this would be nitrite, which is NO2, the -1, +1, 1-to-1 ratio of hydrogen to nitrite. Chromic acid. We have hydrogen, +1, coming from the word acid. Chromic came from chromate, which is CrO4. Look that up, it's got a -2 charge. So our 2 is coming here. 1 is coming there. So we've got H2CrO4. And that concludes the first presentation on chemical bonding. The second presentation will still continue with covalent bonding and looking at structural formulas known as Lewis structures or Lewis dot structures for compounds.